want to guess? Is it point A has the maximum shearing stress? Or is it point B? Or is it point C? Anyone?
Point A.
Point A. Anyone else?
B.
B. Anyone else? C. Okay. Hey, we are engineers. We don't guess. Okay. So some of you think it's C because the thickness is the smallest. Some of you think that it's B, you have more area, no doubt you have a wider thickness. Some of you think that it's A because it's always at the centroid. Yes or no? So the problem with this analysis is what? You have thin wall and you have thick wall. That is where the problem comes. Okay. Now let's try this out. So we're going to remember our 5 rules again. The analysis start from outside in, right? So we are going to look at our shear stress at point C. So this is going to be thin wall, wide flange, analysis. Okay. So the Q at point C. So remember what I told you, that there's only one Q. So you need to put one Q though here. So the Q at point C is width, depth, Y bar. So the width for this case is 30. The depth is 10. Then it's 160 divided by 2 minus by 10 divided by 2. Okay. So this will be equal to 80 minus 5 times 30 times 10 is equal to 22.5 times 10 to the power of 3 millimeter cube, or 22.5 times 10 to the power of minus 6 meter cube. Okay, so 22.5. Okay, so we can now directly find. So once, the most difficult part is finding C, yes or no, right? Once you find, sorry, not finding first moment of area. So from here, the shear at point C is equal to Vy over Izz. I'll draw the global transformation again. I do sincerely apologize. So this is your Y. This is your Z. This is your rotation about X. Okay. So from here, Vy over Izz is common. This is 22.5 times 10 to the power of minus 6. Then we divide by thickness of 10 times 10 to the power of minus 3. Okay. So 22.5 power minus 6 divided by 10 power minus 3 is equal to 2.25. Okay, it's 2.25 times 10 to the power minus 3 Vy over Izz. Okay. So we don't know this is the maximum. Then next, we're going to find the shear stress at point B again. Again, thin wall, wide flange, analysis. Right, again, you have Q. Then the Q at point B is equal to Q at point C plus by the width, depth, and Y bar. Okay, so this is equal to 22.5 times 10 to the power 3 plus by the width is equal to 20 the depth 40 plus 10 is 50. So that the distance is equal to 160 divided by 2. So the analysis is from the outside, right? 160 divided by 2, so is 40. 40 divided by 2, 40. So this distance from here to here, right, is equal to 30, right? So this will be equal to 22.5 times 10 to the power 3 plus by 50 times 50 times 20, 50 times 10 to the power 3, so 22.5. So it's equal to 72. Wait, 160 divided by 2 minus 30 times by 20 times by 50. I think I'm getting somewhere wrong down here. So 160 divided by 2 is 80. So from here to here is 80, right? From here to here is 80. Is it 160? 80. So this over here is 10. Yes or no? 10 plus by 20. 20, 10. Sorry, people. I'm being dumb. Sorry, I got it wrong. Because I divided this way. Okay, so still the top. So this is the area we are looking now. My bad. Okay, so this will be equal to 50 divided by 2. I don't know why I consider the 10 as. Okay, so this will be equal to 80 minus 25 times by 20 times by 50 is 55 times 10 to the power 3. So 22.5 plus 50 is equal to 72. 22.5 plus by 55 is 77.5 times 10 to the power 3 millimeter cube, or 77.5 times 10 to the power minus 6 meter cube. Okay, so that's where we can find our shear stress at point B. So it's equal to Vy over Izz. This will be equal to 77.5 times 10 to the power minus 6 divided by thickness is equal to our thickness is what? 0.02. And then multiply by 1. Why multiply by 1? Because it is wide flange. You don't need to write this, the multiply by 1. I'm just teaching now, okay? So that's why I'm writing it. 0.5 power minus 6 divided by 0.02 is equal to 3.875 times 10 to the power of minus what? Times 10 to the power minus 3. So this is higher, right? This is higher, right? So stress B is definitely higher than stress C. Okay. Then the last one, we need to look at the stress at A. Okay. So the stress at A. So let me copy this whole thing down. So the stress at A, right? So you have to consider both areas now. Okay. So the stress at A is analysis, stress at A, analysis. No way. Analysis is thick wall. Okay, so now the analysis is thick wall. So we have our Q at point A. So it's going to be twice. Okay, so you have to take twice the first moment of area here, right? So 2, the first moment of area of B, plus by this pink section. okay, plus by that pink section. Okay, so plus by your width, depth, y bar for the pink section. So twice first moment of area of B 77.5 times 10 to the power minus 3, or I call it 77.5 times 10 to the power 3, plus by the width, which is equal to 120. The depth is only 30, and the y bar is 30 divided by 2. Okay, so this will be equal to 77.5 power 3 times 2 plus by 120 times by 13 times by 15 is equal to 209 times 10 to the power 3, right, millimeter cube, or 209 times 10 to the power minus 6 meter cube. So from here, your shear at point A is equal to V y over IZZ. First moment of area is 209 times 10 to the power minus 6. And then divide by the thickness. Now the thickness, because it's thick wall analysis, right? So for thick wall analysis, you know that the T is equal to what? 0.12. Right? For thick wall analysis, that the thickness is perpendicular to the what? Perpendicular to the direction of the shear force. Shear force, remember. Shear force, yeah? Shear force, remember that. So this is your thickness. So T is equal to 0.12. So 209 power minus 6 divided by 0.12. So this is 1.7416. Times 10 to the power minus 3 Vy over Izz. So you look at the three values now. Okay, you look at the three values now. You have 1.7417, you have 3.875, all times 10 to the power minus 3, and then you have what? 2.25. Okay, so we know that this over here is less than the shear stress at point B, right? The shear stress at point B is 3.875. So therefore, the shear stress at point B is equal to our tau max. So like what we have done before, the tau max is equal to 75 times 10 to the power 6. Okay, so this will be equal to Vy is equal to 3 point what? We calculated 3.875 times 10 to the power minus 3, right? Vy over Izz. So you find the relationship where Vy over Izz is equal to, so 75 power 6 divided by 3.875 power minus 3 is equal to 19.3548 times 10 to the power, wait, I'm having 75 power 6 divided by 3.875 power minus 3 is 19 point times 10 to the power 9. Unit is Newton per meter 4. So therefore, the shear stress at point A, right, the shear stress at point A is equal to 1.7417 times 10 to the power minus 3 multiplied by 19.3548 times 10 to the power 9. So this will be equal to 19.3548 power 9 times 1.7417 power minus 3. It's equal to 33.710 times 10 to the power 6 Pascal. And the shear stress at point C. So point C is what did you get? Point C is 2.25. 2.25 times 10 to the power minus 3 multiplied by 19.3548 times 10 to the power 9. So this will be equal to 2.25 power minus 3 times by 19.354. 2.25 power minus 3 times by 19.3548 power 9. 43.548 times 10 to the power 6 Pascal. Okay. So this is your answer for your analysis. Okay. So again, as I say, this problem is unique because it combines both thick wall and what? And thin wall. Okay. So